This is practice problem number 1 from lesson 13, solving systems of equations, unit 4. In this practice problem, you are to write equations for these two lines. And when you write equations, look for the y-intercept, so where each line crosses the y-axis, and calculate the slope for each line. Then you can use this form. This is called the slope-intercept form, where y equals mx plus b, m is the slope, and b is the y-intercept. So for equation number 1, which I'm going to call the black line equation or graph number 1, the y-intercept is 2. It's right here. And the slope is 3. So what that means is that for every unit along the x-axis, you go up 3 units along the y-axis. So it's 3 for every 1 unit along the x-axis. That is the same as 6 units along the y-axis for every 2 units along the x-axis. Those are the same ratios, the same slopes. 6 for every 2 units along the x-axis, 3 units along the y-axis for every 1 unit. So it has a slope of 3. For equation or graph number 2, the y-intercept is 8. It's right up there. And the slope is a negative 6 units for every 2 units along the x-axis, or a negative 3 units for every unit along the x-axis. So now it's going in the opposite direction. So you go over 2 units along the x-axis, you go down 6 units. That is the same as going over 1 unit along the x-axis and down 3 units along the y-axis. So graph 2 has a slope of negative 3. Graph 1 has a slope of positive 3. And here I shaded in what we were calling the slope triangles before, just so you can see those relationships. So this is over 1 unit, up 3 units, over 1 unit, up 3 units, and this is over 1 unit, down 3 units, so negative 3 units. Over 1 unit, so positive 1 for negative 3, positive 1 for positive 3, positive 1 for positive 3, positive 1, negative 3, positive 1, negative 3. And so using this form of the equation, y equals mx plus b, m is the slope. We know the slope is 3, and the y-intercept is 2 for equation number 1. For equation number 2, we know that the slope is negative 3, and the y-intercept is 8. So these are the two equations and the two graphs. And here I zoomed in just a little bit so that you could see everything clearly. So this is the y-intercept for each graph, the slope, positive 1, positive 3, and positive 1, negative 3. So it's always the change along the y-axis over the change along the x-axis. So this is a positive 3 over positive 1, a positive or a negative 3 over a positive 1. Before I use the graphs to figure out the solution to the system of equations, or I use the equations to figure out that solution, I like to reason about what that solution is. And it is a way for me to visualize or to see what's going on as I use the graphs and as I use the algebra to solve for that system of equations, the solution to that system of equations. So if you look at these two graphs, one intersects at 8 and the other one intersects at 2. So that difference in the y-intercepts is 6 units. 8 minus 2 is equal to 6 units. And what happens is that 6 unit gap has to close. It has to come together to intersect somewhere. And so the idea is to figure out what unit along the x-axis, at what unit along the x-axis that intersection takes place. Well, that's based on the rates. How quickly are these two graphs moving together? And that's the difference in the slopes. So the difference in the slopes between the first graph and the second graph is 3 minus negative 3. So the slope for this black graph here, that was graph number 1, was positive 3. The slope for this blue graph was negative 3. That difference is positive 6. What that means is that this graph is moving up at 3 units every unit along the x-axis, and this graph is moving in the opposite direction. It's moving down 3 units, so it's a negative 3 for every unit along the x-axis. So that difference is a positive 6 units. They are moving together at a rate of 6 units for every single unit along the x-axis. So their combined rates, positive 6 units per 1 unit along the x-axis. So now if you use that, I have a 6 unit gap. I close that gap at a rate of 6 units for every unit along the x-axis. So how many of those 6 units can I take out of these 6 units along the y-axis? Well, it's 1 time. That positive 6 along the y-axis divided by 6 units for every unit along the x-axis. 6 divided by 6 is 1. So that's 1 unit along the x-axis. These two graphs are going to move together by 6 units. And once you know that the x-coordinate is 1, then you can use that value in either of these two expressions to figure out the y-coordinate. So 3 times 1 is 3 plus 2 is 5, or a negative 3 times 1 is a negative 3 plus 8 is also 5. So the intersection of these two graphs is at the coordinate pair of x equals 1 and y equals positive 5. Now that means that that is the only coordinate pair that has the same x-coordinate and the same y-coordinate for both graphs. Now there are lots of places that have the same x-coordinate. So for example, right here, these 2 points have the same x-coordinate, but they have different y-coordinates. And likewise, there are lots of places that have the same y-coordinate. These 2 y-coordinates are the same for these 2 points, negative 4 and negative 4. But they have different x-coordinates. This one goes out this way to negative 2. This one goes out this way to positive 4. But that solution right here is the only place where the coordinate pair is the same for both graphs. It's a positive 1 for the x-coordinate and a positive 5 for the y-coordinate. So that is the solution to this system of equations, the only place that has the same coordinate pair for both graphs. The solution to a system of equations is the intersection of the graphs for each of those equations. It is at that point that y has balanced each expression so that they are equal. Think about those hanger balances that we started with in this unit. Imagine that you know the x-coordinate, the value for x, and now you're moving along the y-axis on that x-coordinate. And you're finding the place where the y-coordinate, the y value for y, balances those equations or those graphs. That is at the intersection. So now we're going to solve this system algebraically using the equations. And remember that we reasoned through it a moment ago. We found the difference in the y-intercepts and the difference in the slopes. So because y has balanced both expressions, they can be set equal to each other. So y is equal, and so now both expressions are equal to each other. And when solving algebraically, look for the difference in the y-intercepts. Look for the difference. You're going to calculate 8 minus 2 somewhere when you solve this algebraically, and look for the difference in the slopes or the rates. You're going to calculate 3x minus a negative 3x somewhere as you go through this solution algebraically. So the first thing I'm going to do is get rid of this positive 2 on the left side by subtracting positive 2. Well, I also have to do that to the right side. Positive 8 minus positive 2, that is the difference in the y-intercepts. That is right here, 8 minus 2. And so you're left with 3x equals a negative 3x plus a positive 6. And so now what I want to do is get rid of this negative 3x right here, because I want to get this down to where it's just x on one side and just a value on the right side. So subtract this negative 3x. So negative 3x minus a negative 3x, that's 0. And then on the left side, it's 3x minus a negative 3x. Well, that's the difference in the slopes. That's right here, 3x minus a negative 3x, the difference in the slopes. And notice that this 3 and this negative 3 are separated on a number line by 6 units, and that's a positive 6 units in this case. So this is a positive 6x equals a positive 6, which is what's left on this side. Now this positive 6 is the difference in the y-intercepts. This positive 6 is the combined rate as those two graphs move towards each other. So how many of these positive 6's from the combined rate can I take out of this positive 6, which is the difference in the y-intercepts? A little bit weird to look at because both values are the same. But the answer to that question is 1 time. So 6x divided by 6 is going to be x. And 6 divided by 6, I can take 6 out of 6 1 time. What that means is that for each unit that you move along the x-axis, these graphs come together by 6 units along the y-axis. That's the combined rate. Well, they're only 6 units apart on the y-axis. So in 1 unit along the x-axis, they're going to intersect. So the x-coordinate is 1, and the y-coordinate you can calculate by using either expression. 3 times 1 is 3, plus 2 is 5, or a negative 3 times 1 is a negative 3, plus 8 is also 5. So this is the coordinate pair for the solution to the system of equations, or the graphs. So the x-coordinate is 1, the y-coordinate is 5, and this is the only place where the x-coordinate and the y-coordinate are the same for both equations and for both graphs. It is the intersection. It is the solution to the system.